Hello, everyone, and welcome to Generative Geek. I am Vaibhav, and I am excited to bring to you a brand new series all about embeddings. Embedding is a fundamental concept in natural language processing and AI. And with the growing adoption of LLMs and developers wanting to build LLM apps, it's crucial that we understand what embeddings are and what are the various use cases of embeddings. Over the next few videos, I'll dive deep into what embeddings are, how they work under the hood, and most importantly, how you can harness the power of embeddings in your own projects, be it LLM apps or be it NLP projects. It's up to you. Once you understand the concept, once you understand what tools are required to generate embeddings, how can you store embeddings, it's up to you what projects you want to use those embeddings for. So what I've done is I have created a three-part series. In video one, we'll start with the basics. What exactly are embeddings conceptually? Why they are so critical for AI to understand human language? I'll walk you through some intuitive examples to really solidify your understanding. We'll then get hands-on and I'll show you step by step how to actually create embeddings yourself using OpenAI libraries and then use open source libraries to cover a very useful use case of embedding, which is search, right? So then in video two, we'll take two other use cases of embedding. First is we'll use embeddings and we'll generate recommendations out of them. So how do you build recommendation system using embedding as a concept, right? And my objective here is to help you understand the concept, not build a production grade recommendation system here, right? We'll probably get to it in a future project video. We'll also cover zero shot classification with embeddings. Now, zero shot here refers to doing classification without any pre-labeled training data. So generally, as a student of ML, you would have seen that classification is a task where you train a model with lot of labels and with lot of labeled data, and then the model learns how to predict the labels with once the training is done, it is able to predict the labels for a future test it is given. This what we'll do with embedding is a more of a zero shot classification. Finally, in video 3, we'll cover more advanced topics like, using vector databases. Now, vector databases is gaining a lot of momentum thanks to LLMs, right? You have to store those embeddings somewhere, and vector databases help you efficiently store and search embeddings at scale. We'll go over the best practices and tips and what I have learned to get the most out of embeddings in real world application. So without further ado, let's get started with video 1 now. So let's get started. And because the first what I want to do is I want to help you conceptually get strong idea about what embedding is. Now think of it like, what embedding does is it takes text input and then converts that text input into numerical representation. So look at the screen and you can see, hey, there's an input text like, hey, what's up? You send it to some kind of an embedding model. And that model, it outputs a lot of numbers. Now, depending on how the model interprets that text, it then sends you out a bunch of numbers, right? Those numbers will not make any sense to you, but that's what embedding, if you look at just the application part of it, that, hey, what is the embedding model doing? It takes input text and just converts it into a lot of numbers, right? And what it actually is doing under the hood is that it takes the input text and it then maps it into a dense multi-dimensional vector, right? So you gave it like 5 characters, right, or 5 words, but it then takes those 5 words and converts them into a huge list of numbers, right? So but what do these numbers generally interpret, or what do they correspond to in the real world is the model's way of placing that text in that vector space. So imagine that, there is this vector space and your model is going to throw numbers which will plot that text somewhere in that vector space. It's an infinite vector space. So how do you decide where a word will go? Now that's basically a function of, or where that stream of words will go. That's a function of how the model decides its place in that vector space. That decisioning is what you call embedding. Like, if I have to like really say it in a layman way. What is a very important concept with embedding is that, similar words, and now similar here doesn't mean same. Similar here basically means it's related in the form of context and intent. So school and a place to learn, these are two different words, but they can be related, right? Because their meanings are similar. So the embedding model is largely able to derive the meaning out of the text and not just treat text as, a bunch of words put together, right? So it is able to understand what is the text trying to say. Not understand, but put it the model is built in a way that when it will create those embedding numbers, right, the numeric representation, it will fall in a place where two similar text will be very close to each other. That's the job of the embedding model. And if you are like, dissimilar words, you will see that they will appear further away. Now, let's just take an example. Like, if there is, like, what I have tried to do is through this visual, if you have clothes and sunglasses, and this is like a vector space, you will see that their embeddings will be still somewhat away, but still more closer to each other than, let's say, books and student and school, right? Same with music system. It might actually be further away from all of these. So you give it the word and it'll say, hey, books, you go there. Student, you go there, right? Clothes, you are in that coordinate, right? And this is a high dimensional space. So this is not like a 2-dimensional X, Y axis. This is like, tons of axes. So in that, you are putting the word somewhere, right? And that's what the embedding model does. And in that process, what it is able to do is that words with similar context and intent, they appear closer, and words from different domains are further away from each other. That's what the embedding model is able to achieve. And, you might say, hey, okay, what's the great thing? When I was doing ML or when I was studying ML, or I have at least just heard about things like bag of words and one hot encoding approach. What is so special about it? And the thing is that, traditionally, while one hot encoding and bag of words has been the way to go, both of these techniques suffer from the challenge of understanding the semantic meaning, right? So one hot encoding, you might remember, or if you don't know, it builds sparse vectors, and in the process, it fails to capture the semantic meaning, the relationship between words. One hot encoding, there is also no way to measure similarity. What one hot encoding does is the vectors are orthogonal and they do not capture any semantic relationship. And also, as the vocabulary size grows, like, it's like, hey, each word is a column. If you have to just think about it, each word is a column in an Excel. Now, as your vocabulary grows, you have to keep opening new columns, right? And then when the new sentence comes in, you just keep marking 1 or 0 depending on whether that word appeared in that sentence or not. So as the vocabulary size grows, now think about it. If you have to keep opening, new columns or new dimensions, as it's called in machine learning, it will lead to what is called the curse of dimensionality, and it will make it difficult to work with large data sets. Now, one hot encoding cannot represent words that are not present in the predefined vocabulary. So if it finds a new word and it's not there in the vocabulary, it's like, hey, I have no idea what you mean, right? So there's a limited flexibility and adaptability to new data when it comes to one hot encoding. With bag of words, it has a very different problem. It's like, hey, I disregard the order and context of the words in a sentence. It's just bag of words for me. It's like, a girl went to school. It's like whether it was girl, school went, or a girl went to school, both of them are same for me, right? So, it loses the context of the words in a sentence. It treats them as independent entities, and the syntactic information that is conveyed, because when you group words in a certain way together, that is lost, right? So grammar and structure goes out of there's no way you can have grammar and structure in such a representation. And again, the resulting vectors, even in bag of words, are very sparse, especially for large vocabularies, leading to high dimensional and inefficient representations. Again, this is also very sensitive to vocabulary size, right? So these are, guys, the challenges. Now, I hope you understand what we are trying to do here. Now I want to get into the coding part of it. So let's just get into the coding part of it. So now let's get started with the coding part. What we'll do is I'll just open up a new notebook and we'll call this notebook generating embeddings.ipynb. And what we'll do is I'll just write down some text here. So what we are going to do as part of this notebook, and I'll do the coding step by step with you. And if you are following, my sincere recommendation is that you do the coding along, or you pause the video in between, try to do the coding yourself. That'll give you a lot of confidence, right? We'll cover three things in this. I'll demonstrate what generating embeddings using OpenAI model look like. How do you query text and similarity of it with a corpus of text? And how do you compute cosine similarity for a product description? This is the search use case, and it will help you understand what I'm trying to do. So what we'll do is, first steps first, I think I need to generate, install few libraries. So create requirements.txt, and the libraries we will go out and install are OpenAI. We'll need scikit-learn. We'll need matplotlib. And let's start with these for now. We also need python.env. And then what you can do is you can go to, if you are on a Mac, press Command Shift P and go to Python select interpreter, right? Now here, what you can do is you need to select. I recommend that you be on Python 3.1110 and above. I have 3.11.9, so I'll use that. And what happened? So create a virtual environment. I'll create a virtual environment. Sorry, I was wrong there. I selected. What we'll do is we'll create a virtual environment with vn, and I'll select Python 3.11.9. Now it sees that there is a requirements.txt, and in Visual Code it will automatically ask you, hey, do you want are there any dependencies you want to install? At this point you can just select and say okay. So now it will start installing those dependencies as well. It'll take a little while. You can see logs. It is creating the environment. So this is the terminal which gets open, and you can see that it's trying to do some things. Once it's done, what you can do is you can go to terminal, open new terminal, and if you see .venv in the brackets, that's basically a sign that things went well, right? I have covered this in detail in one of the other videos, video 1 that we produced a couple of days ago. If you have any doubts in this, I recommend you go back to that and look at it. Next, what we want to do is we want to have we'll say import OS. Once all our libraries are installed, we'll say import OS, select Python. I'll import .env, import from .env, import load.env and find.env. And at this point, my recommendation is just run this cell, right? When you run this cell, it will say, hey, which kernel source do you want to use? So I'll say Python environments, and at this point, it will tell you, hey, there is a recommended environment .venv which we created just now. I'll select that, right? Okay, this is a new environment, so it is asking me to install a few things, which is okay. Once that is done, what you can do is you can say load.env, find.env. Now what this, okay, it did not find the .env file, therefore we got a false. What you can do is you can come here, create a .env file, and over here my recommendation is, what you need to do is have a variable called OpenAI key, and you should put in your key here, right? Whatever is your key, I'll suggest you put that key here. For the purposes of this video, what I'll do is I'll just go out, create a key for you, and we'll use that key. And before I publish the video, I'll be sure to just invalidate the key. Oops. Or let's just do this. I'll just put in the key, and then I'll show you the key, just because I want you to learn how to use these things. But I'll invalidate before I publish this lecture. So you put the OpenAI API key and save this .env file, come back, run the cell again, and it'll give you a true. This means it found a .env and it's okay about having found it. Now what we'll do is I'm just going to copy paste some sample text. Now this notebook will be available to you as part of the description of the link on my GitHub. You can use this or just paste any text, right? What I've done is I've just taken some news about Copenhagen and just put the sample text. Now this is the text that we'll use for generating embeddings, right? When you the library we are going to use for generating embeddings is the OpenAI library, and therefore I recommend what you do. You go to platform OpenAI Embeddings. What you can do is just do a Google search saying OpenAI Embeddings. The first result is generally the result we want, right? And you can see here, if you come here, you will see that what are embeddings used for and all of that, and they're given some examples. But there are three models, right? So they have a text embedding 3 small, text embedding 3 large, text embedding ADA 002. Now it's up to you which model you want to use. For the purposes of this video series, I'm going to use a text embedding 3 small, largely because it's able to do a lot more work with a high accuracy, with a high performance on for cheaper cost, right? So text embedding 3 small is what I'll use. Going back into the coding environment. Once you have your text entered, what we'll do is we'll start importing the libraries. So from OpenAI, import OpenAI, and at this point what I'll say is also have instantiated OpenAI client is equal to OpenAI. If you have your .env file there, .env has found your .env file, then you don't need to put the API key. Otherwise, you will be required to put the API key here. You need to have this thing does the same thing. If I just say two were given, sorry. So OpenAI client. Now what we'll do is we'll select what model we want. So I'll just put the model name, text-embedding-3-small. That's the model I'm going to use. And now let's just create a response to generate embeddings. Now I'm also using GitHub Copilot, so it's giving me a lot of auto completions. And if you use GitHub Copilot, it's great. It's sometimes, if you know what you're doing, it's a great tool, right? So it tells me, hey, this is the method, text_embedding. This is probably not the right method. What I'll do is I'll OpenAI_client .embeddings.create. This is what we want, right? And we pass in the model. Model is equal to model. Text is equal to sample text. Now this is right. So I'll just say not text but input, and we'll run this. It'll take a little while. Now what has happened is, if you look at the type of response we got, it says it's a create embedding response, right? So we got a create embedding response back from OpenAI. Now what I'll do is I'll create a dict and I'll dump the response in the dict into a dict. So let's see. Once you do this, a logical step whenever you have dicts is, before you start printing them, is to just see what keys do we have, right? So if you look at these dict keys that come back from the model, there's a data, there's model, there's object, and there's usage. Let me just print the dict for now. It'll give you a sense of what all has come back. Like I was telling you in the intro videos, it converts a lot of those texts that it gets into bunch of numbers, right? So look at this, what we have got back is, we gave it some text, we gave it this text, right? And we said, hey, you know what, create embeddings, use this model, which is text embedding 3 small, but generate the embeddings. And it has come back saying, hey, you know what, this is the embedding I have got for you. So it's a dict where, we saw the keys. There's a data key. Within the data key, there's a big list. And in that list, there is the first key called embedding. And within that embedding is where you have all the embeddings, right? The entire embedding response is there. So what we'll do is we'll just try to print the embeddings, at least few embeddings, right? And there was one more key that we got back was model, right? If you just do it, it'll tell you, hey, you know what, text embedding 3 small was used. So there's another key that we saw, which was usage, right? So what we'll do is we'll just say, hey, what is the usage key all about? Now, if you look at the usage key, it tells you how many prompt tokens were used, how many total tokens were used. So as part of generating this model, 242 tokens got used. Now let me just print first five embeddings, right? And we saw that in response underscore dict, there was a data key, and within the data key, there was a list. So we'll just grab the first element of that list, and within that, we had a key called embedding. That's what we saw earlier. If you don't remember, just scroll up, and you can see there's data. Data is a list, and within the list is the first element has the key called embedding, which has the entire list, right? So we'll grab that and we'll say, hey, just print the first 5, right? So print up to 5. And you can see, we got the first 5 numbers. If you just want to figure out, hey, what is the total length of this embedding, we can say len response underscore dict data 0 embedding. Yeah. And you see it's 1536. Now that's the number that OpenAI will always respond back with. So these, irrespective of what you send it, the open embedding model always have 1536 characters, 1536 list elements, right? So that's how long the embedding model response is when it comes to open embedding. Now, so what we did is, till now, just to recap, we got a lot of text, we got some text, we generated embeddings for that text, and this text is just, if you want to have a look at it, it's about once inundated with cars. Copenhagen is now the world's most bicycle friendly capital city. Its transformation, it's a cycling city. There was a movement because there was pollution and whatnot, right? So you get a sense of what the article is trying to do. Now that's the beauty of human intelligence. Just with very little information, you can understand what it is trying to say. What I'll do is, I have pre-built 3 texts. What we can do is, I'll not use that. I'll just take this, come back to this, go to Claude.ai, and I'll say, I'm going to give you some text. I want you to give me semantically similar text with different phrasing. Now let's see what it comes back with. I'm asking Claude to give me text which is semantically similar, but phrasing is different. So let's see. It's typing out some things. I'll just take that. Okay. And we'll go back and we'll say, I'll save this in a text called text for similarity match 1. We'll do 2 texts, so you get some sense of what we are trying to do. So I just copy pasted whatever it gave me. Here's a semantically, okay. and we'll have one more text where we'll ask Claude to give us dissimilar text. If you think the speed is slow, my recommendation is maybe move it to 1.5 and watch. But don't skip. We are covering some really interesting stuff here. Once this is done, okay, what happened to Claude? No worries, I'll give you some text. I want you to create text that is completely opposite. Use different characters. Use different semantic meaning. Now let's see, it's saying Pyongyang, the capital of North Korea, was once a city filled with cyclists and all that. Now let's see, let's use this, right? So I'm going to use this. We now have two different texts, right? So we had our original text, which was about Copenhagen being a cycling city. Then we created some other text, right? You know, some made up text. And it's not the same text. It's probably similar, but it's not the same text. Now it's for the machine to figure out, does it know the meaning or not, right? So, and then we have another text which is probably about Korea, North Korea. Our job now is to say, hey, you know what? If we create embeddings for these two, what I want to do is, if you understand what I'm trying to do, I'll now create embeddings for text for similarity match 1 and text for similarity match 2. And then we want to see if those embeddings are closer. Like, you know, like I said, if two sentence structures or if two sentences have related or semantically similar meaning, they will fall in the vector space, they will fall more close to each other. When you say they fall more close to each other, what you are actually implying is that their distance is less, right? You know, so they are closer, their distance is less. So we'll bring in some notion of distance calculation in a while. So if those embeddings are closer, their distance will be less when compared with the embeddings of the sample text for generating embeddings. Now, this is the beauty of Copilot. It knows what I mean, what I'm trying to type, right? So this is what we are going to do, right? You know, we'll now use both those both the similarity searches that we have, both the text that we have created. We've just asked Claude to generate, and we'll now create embeddings from both of those. So in order to make things easy for us, what I'll do is I'll create a function first. We'll create a function diff create embeddings from text, and this function will take some input and it will take a model. The default model is text embedding 3 small, and it is already doing a lot of work for me. So I just need to see whether it did the right thing or not. So OpenAI client.embeddings.create, this time it got it right. Model is equal to model, input is equal to input, response dict is equal to response dot model dump, return response dict. Instead of returning response dict, what I want is I only want the embeddings to be returned. So if you remember, otherwise you can just go back up because I remember it. So I'll just start typing. Response dict had a key called data, and within that data, the first key had this. But now there is one trick here. The trick is, because we were only giving it one text and not a list of texts. You know, if you had given it multiple texts, it would have given very different answer. So the 0 won't apply there. So what we'll do is we'll say, hey, return and data embedding. We'll say return data embedding for data in response dict data. So what we are saying is that data has a list, right? And we were basically using the first element of the list. But this, if the input itself was a big list and not a single item, then the answer will be a list. I can send multiple texts for, OpenAI's embedding model has this capability. It can take multiple, it can take a list for embedding. It need not be a single text for embedding. I could have done text for sample generation, text for similarity match 1, text for similarity match 2, all in one go instead of doing one by one. And I'll show you that, right? So what we have done is we have just created this function which will create embeddings from text. Now let's get to the real work where we'll generate these embeddings, right? So embedding for sample text is equal to create embeddings from text, sample text for generating embeddings. Now I just want to show you that, we earlier generated some embedding. I want to just show you that, that those embeddings and this embedding are same. So the output we are getting, the first 5 is 0.02255, and we got this output earlier, 0.02255, 0059, 0399 in the end. And if you look at it, both are same. So our function seems to be doing the job right? And the other thing with embedding models is, if you give it the same text, the embeddings are always going to be same, right? At least that's how the model is designed. Now let's do embedding for similarity match 1. We are going to pass text for similarity match 1 here. Next, do embedding for let's see, similarity match 2, and we'll do this, right? So next what we'll do is we'll just print the first 5, embedding similarity match 1, print embedding similarity match 2. The Copilot is able to understand, because we've already written some code, it is able to understand what I'm trying to do. And if we do it, we get like 2 prints, right? The first line is for similarity match 1, the second is for similarity match 2. Now what I'll do is I'll show you that, if we send embeddings for all, right, for all similar text, and we use the method that we created, which is create embeddings from text, and we pass it a list instead of so text for similarity match 1 and text for similarity. One good thing about Copilot, if you use Copilot, is that if you name your variables right, it knows what has to be, what it can guess more correctly, right? If I had not given this similar text, it might have just taken the sample embedding as well, the sample text as well, right? If I had just named it embeddings for all, right? So name your variables right, and Copilot is able to guess a lot of stuff. So create embeddings from text, text for similarity match 1, text for similarity match 2. We'll do that. And now if you look at what we'll do is, I'll just say embeddings for sample, embeddings for all similar text, and I'll print the first 5, right? So if you see 0.02550, so what I've done is it gave me back a list, and in that list, if you want to just see what type it is, embeddings for all similar text, it's a list, right? And if you want to see what is the length of the list, the length is 2. So what we are doing here is that we are taking the embeddings for all similar text, going to the first element of the list and printing out the first 5 elements. Similarly, we can do like, we can take the first element and print out, I forgot the print. This is Jupyter, so it needs a print. And we'll print this, and we got 0.0255. If you look at it, both are same, right? So what I demonstrated just now is that it's up to you. You can send one text, like, one paragraph, or you can send a list of text, right? And it'll do that batch work and send it back to you. But the other thing, 1536, you remember the number of elements? Let's just do a len on embeddings for all similar text, the 0th element, and you will see it's again 1536, right? if I do for the first element, for the second element, again it's 1536. So like I was saying, it's an OpenAI model output which always gives 1536 elements as part of the embedding response, right? So that's what it is. Now we have these embeddings, and what we want to now do is, our job now is to find the distance, or how distant it is from the original text. Our original text was sample text. What we'll do is write a function which will compute distance of the embeddings we generated, of the two embeddings. Let's just say of two embeddings, right? Using cosine distance. So what we'll do is, first step, we want to calculate the distance. So let's have a list, empty list called distances. And now from scipy dot spatial, we'll import distance. Once you have this, what I want to do is, for embedding in embeddings for all similar text. So this is our list, embeddings for all similar text. I'm taking one embedding each time, and I'm appending it to the distances list I just created. There is this distances.cosine. We are trying to find the cosine distance. So embedding for sample text 0 was our embedding that we generated for sample text, and we are passing it the embedding, right? The similarity embedding, right? So we'll pass that and it'll get appended into the distances. Next, once this is done, we want to print the distance. So print distances, right? So you can see the first one has a very low distance, the other has a higher distance. Now low distance means more similar. So let's just see, 0.05 is the first one. The first one for us was Copenhagen, capital of Denmark, was once a city congested with automobiles and all of that, right? Similarity search 2, Pyongyang, has come out farther away, right? So you can clearly see that it was able to figure out. And if you want, we can even do this, where we can ask Claude to now generate some random text. Generate random text about Copenhagen. 200 words, right? So let's see. It will generate some random text about Copenhagen. The city that blends charm of historical roots situated on the eastern. Let's just see, right? What I'm trying to do here is trying to show you that, hey, it's not that you can give it any text if the meanings are not similar. If there is no relatedness in terms of context and intent, then it should not work, right? So, and what I'll do is I'll add code here, call it text for similarity match 3. Text for similarity match 3 is equal to and we'll paste in this text. And what I'll do now is I'll just take I'll create another I'll append this list here. I'll update this list with the third element as well. So this will be text for similarity match 3. So now we have three items in the list for which we are creating the embeddings. If you want, I can just print embeddings for similarity match. Right. So now it again gives me 5 elements from this. And if you now look at the length, it should be 3. Oh, length is same, 1536, sorry. Now let's see. If you look at it, the text that we generated now had Copenhagen and maybe the cycling and all of that. But this is the text that we generated. Copenhagen, the enchanting capital of Denmark, hub of culture, home to the Danish royal family. It has a lot of stuff about Copenhagen, but But if you look at the distance, it's farther away from the Pyongyang distance, right? The article about Pyongyang where it said it was once a cycling city and all of that. So when the model is creating the embedding, it's saying, hey, you know what? I'll put the Pyongyang or the text for similarity match 2 more closer to the original text, right, than the text that you have given in similarity match 3. So this is what we have just done. Now what I'll do is I'll help you. I'll take a real life example around product search, right? So let's do a product search example where I'll product search using embeddings. And again, in this, the method is still the same. So let's say you have a scenario where you are given a catalog of products and a user wants to search for a product, right? So I'm just making this up. We can use embeddings in such a case, right? The overall approach remains the same. And what is that approach? You will generate embeddings for the product catalog. You will generate embeddings for the query. You find cosine distance between query and catalog. Print top 3 closest products. Okay, so this is what we are going to do. We'll generate embeddings for the product catalog, and I'll probably ask, I already have. Let me just use Claude again, right? So I don't know why it's not giving me. I need your help with generating a random product catalog. Your catalog needs to be a list, to be a Python list. Each element in the list has to be a dictionary. Keys for the dictionary are title, description, price, category, features. Features will be a list of key features of the product. A sample product list will look as follows. Let me just give it a 2-string list that I have. So what we are doing is we are giving it a list, and I'm telling it I want you to generate a 40 product or let's say a 25 product list. Let's give it this task and let's see what it comes back with. I'm really hopeful that it'll okay, it's unnecessarily put fashion category. It was not required. Now it's probably just going to go only with fashion. Okay, but what I have done is just before starting this video, I had already created one list. I'm going to copy paste. What you can use the similar method, right? You can, and I did the same thing. I did not go out and build the entire list by my hand. I just asked Claude to do it, and it made some random stuff. So we have this products list. I have used 3 categories here. There's one fashion, there is electronics, and there is grocery. Right, so for each of these products, we have a title, we have a description, we have a price, we have a category, and we have features, right? And this is all made up data, so don't be like, after me if you find that, hey, organic herbal tea cannot be caffeine free or things like that. I have no idea. I just asked it to make data hub, right? So, and let me just see how many products are there. That I don't remember. So I think there are 19 products in this. Okay, so there are 19 products in this, and what we are going to do is we are now going to create embeddings of products. So when you look at products, right, if you look at a product catalog, it has various attributes. Now one way is that, hey, you know what, I'll just create embeddings of the titles. That's one way. But a far smarter way is that, you don't just create embeddings of titles, rather you pick useful attributes like, title, description, features, category. All of these are useful attributes, and therefore my suggestion is use all of those attributes, right? Instead of just doing the titles. So what we'll do is we'll create a function which will help us generate product info text, because these are all different attributes. We want to merge them into a single string, so that then we can pass that string saying, hey, you know what, this is product data, and just give me embedding for this data. So I'll create a method, we'll call it def create product info text, and it'll take a product, and what it'll do is it will return a f string of the various attributes that we have, right? So we'll say title and product title, then we'll say description and will be product description, category and product category. Next we'll say features, and because features is a list, and see how smart Copilot is, I was about to come to this point that, hey, features is a list and therefore we will need to join it, but it has already done the job for me. It has used a comma. We can use any delimiter you want. You say, hey, you know what, we don't want to use comma, I want to use semicolon, and that's also okay, right? So this is the product info text that will come out. And then what we'll do is, with this method handy available, what we'll do is we'll say product infos. So we'll take all the products we have, we'll create product infos, we'll pass create product info text product for product and product. So instead of doing a loop, it has done a list comprehension. Otherwise, one way is that, you loop through each product and then you keep calling product info text and you keep appending it to product infos list. So it has done the same thing as a list comprehension. Next, once you have the product infos, you want to create embeddings of those. So here we will use create embedding from text that we already created, and we'll pass it the entire list of product infos. I have already shown you how it works with the list. So now just run this. It will take a while, and it's ready. You want to see embedding for what is the length? You want to see that it's 19. So we passed it 19 products. We got back embeddings for 19 products, right? Next, what we want to do is we want to have like a product query. So let's say my product query is makeup. We have fashion, we have electronics, and we have grocery. So my thing is best coffee for breakfast, right? Let's just say, right? I don't even know if we have a product with that description there or not. What is required is we'll now create an embedding for the product query. So create embeddings. The other thing is, if you write meaningful text, like I did when we were doing the product thing, we'll generate embeddings for product catalog, we'll generate embeddings for the query, cosine distance. GitHub Copilot can read all of this and it can suggest you already that, hey, this is the next logical step to do. So embedding for product query is therefore the next logical step. Like, we already did embeddings of the catalog. Now this is the query that came to us. We are generating a embedding for it, right? So when you are creating embedding, and this is a single item, so I'll take the 0 here, right? Now, so I want the first element to be part of this embedding, right? Now it has done. next step is just say distances. We'll just start computing the distances the same way that we did earlier, where we have embedding for products. So these are all embedding for products. This is a list of 19 elements. So it will take each element one by one and it will append into the distance.cosine embedding for product query. This is the query and this is the embedding, right? And what we can do is then we can say, hey, you know what, print the distance. Or what we can do is we can say, I want to print the top 3 products, right? So we'll import numpy as np and we'll say indices. What I'm trying to do now is I'm sorting it based on the distances, and we'll take the first 5, right, or first 3. That was the objective. We'll take the first 3. We are basically saying, hey, you know what, this is the product query that came. We created an embedding of it. We have the product catalog embedding already with us. Now we are looking at the cosine distances between that embedding of the query and the catalog. And whichever are the top 3 lowest distance products, I want you to print those, right? No, I'm trying to find that. So for index in indices, we'll say print. Okay, see, it is able to figure out what has to be done. So print product index title. So from that products was the list, right? You know, which was the original list that Claude gave us, and we pasted that. Print products index title. What is the description? What is the price? What is the category? What are the features? I also want to print the distance, right? You know, so what I'll say is, what is the distance? And the distance is in the distances. So distances index, yeah. So this is what I want to print out. Sometimes it gets irritating, but part of life. So yeah. Yep. So you got it, guys, right? Now, so what I'm doing is I'm just printing out the top 3. Our query is best coffee for breakfast. Now from that, it says organic coffee beans, premium Arabica coffee. These are the features. What I'll do is I'll say I could have used a better way of printing, or maybe we don't even need all the descriptions and features. I'll comment this. So let's see. So we got 3 results. The first product is organic coffee beans. Distances index. What went wrong? Why did it not print the distance? Distances. Distances. Something is wrong here. Let me just see. Oh, sorry. This is not an F string. That's the problem. Okay. So the distance was to the original query. This distance is 0.57. If you see eggs is coming at 0.72. Organic herbal tea is not coffee. All right. So tea is not coffee. So it's coming even further away from eggs, right? We probably don't have that many items in this 19 catalog product set. But let's say if I say best bread, right? Or bread and cheese, right? Now let's see. It's giving me artisan bread assortment, gourmet cheese selection, assorted fruit basket, right? And you can see how the distances are increasing. So this gives you a good sense of how the model is. A model is basically finding meaning within the text. Now, one important thing I want you all to understand is also around visualization. So I'll just do one last section on visualization of similarity. This will what we'll do is we'll just plot using PCA, principal component analysis. What we'll do is I'll take all these components and we'll plot it using matplotlib. So from sklearn, and that was the reason we imported scikit-learn earlier. So from sklearn dot decomposition import PCA, import matplotlib.pyplot as PLT. We'll also need sklearn.cluster import k-means. If you're not able to understand this code, that's okay. My goal here is to just help you understand how to visualize. I want you to, I'll take these embeddings and I'll show them on a visual, right? Now that's what I'm trying to do. So the first step is dimensionality reduction. Now these are like 1536 dimensions. We want to reduce them. So we'll reduce them to 2 dimensions because x and y axis is what we want to project them onto. Project them onto a 2D. Okay. Reduced embeddings is equal to PCA fit transform embedding for products. Now here I just need to say, embedding for products. That's the embeddings that we calculated for each product. 19 products. We get reduced embeddings. Second step is we'll calculate the distance. In this case, what we can do is we can use the Euclidean distance. So from sklearn.metrics pairwise import Euclidean distances, and distances is equal to, now distance calculation has various ways, reduced embeddings. So we'll calculate distances between these reduced embeddings. So what we did is we took the product embeddings, we reduced them to a lower dimension. From 1536 we brought them down into 2 dimensions, and when you do such things you obviously lose information. But one beauty of PCA is it is able to find which are the most important features and use them only, right? So so while it's lossy, you still are able to retain most of the information, or most vital pieces of the information are retained, right? And then once you get that, we are calculating distances. Next, what we'll do is we'll cluster them using k-means. We have 3 categories. I know that in k-means you have to actually give how many clusters you want, because we know that we have 3 categories. I'll give you 3 clusters for now, and we have to just run k-means.fit reduced embeddings, labels is equal to k-means labels, and now next step is just visualizing the clusters with matplotlib, right? So next step is we'll just start visualizing PLT. We'll do a scatter plot. We'll say reduced embeddings, all the first axis, the second axis 0 and 1, labels CMap we don't need, so we can remove this, we can be till here, and then plt.title product clusters, or you can say product embedding visualization. Next we'll say plt.xlabel principal component 1, plt.ylabel principal component 2. Then we'll do the actual annotation for I comma product and enumerate product, plt.annotate product title, reduced embeddings I0. Okay, and then last step is plt.show. So once we do this, what we are now trying to do is so look at this, guys. So we gave it these 19 products, embeddings got created, and those embeddings were in very high dimensional space. They were in that 1536 dimensions. We brought it down to 2 dimensions now, x and y, using PCA, and you can see how beautifully all the electronic stuff is together, all the fashion stuff is together. Even within that, the warm winter scarf and the stylish sunglasses are like far off, but they are still together as a cluster, and all the grocery stuff is together. Now just to show you even better, what I can do is I can make the clusters instead of 3, I'll say, hey, I want 6 clusters, right? So let's see what happens. So here you can see it has done different color coding. Now all of the electronic is still together, but the warm winter scarf, maxi dress, the dresses, clothes go together. The sneakers and sunglasses are now in different clusters, right? Organic coffee and herbal tea are together, but the fruit basket and some other, sorry, this is like slightly cluttered. Gluten-free pasta and plant-based burger patties are in another cluster. Though all of them are like, if you reduce the number of clusters, they are in the same cluster, but they are still far off, right? That is what I meant when in an earlier video, I showed you that, hey, the two things can be still close by, but they will be away from each other. They will not be same. So this is it, guys. This is what I wanted to show you as part of this video. We started with, and you can do it with TSNE as well. I have done PCA, but you can do the same with TSNE as well. So what we did as part of this is we took some sample text, we generated embeddings. I'll just quickly go through. We took some sample text, we generated embeddings. Then we used the concept of, we saw how many tokens were getting used. We have taken the model text embedding small 3. Then what we did is we took some text for similarity match 1. We generated another text. We used Claude for most of it. You can use anything you want. Idea is that generate similar text or dissimilar text, right? And then we generated the third dissimilar text, like completely random text. And we could see how even when it had Copenhagen, and then we created embeddings from those texts. We created functions for it. We saw that, when you pass a list, you get back a list. When you pass a single element, you get a single element. You don't get a list, right? So you get a list, but it has only one element. And then what we did is we found a way that, we can use scipy.spatial distance.cosine is how we calculated the distances. Next, we took a real life kind of a use case where we said we have a product catalog and we created embeddings using various attributes of the product, not just the title. We could have done just with the title, right? And it would have given very different search results. Because the information will also be less. If you look at it, if I just give it smartwatch with GPS without any features, heart rate monitor and all, tomorrow if there is any health appliance kind of a query, smartwatch with GPS will probably not feature there, even though it has a heart rate monitor. So that's the beauty of adding more features or more attributes. For that, we created a method called create product info text, which had title, description, category and features. And then we calculated distance between the query text and all of the product catalog embeddings. And in the end, I showed you a way of visualizing similarity. As part of this video, I'm going to also paste link to the notebook. Have a look at it. I hope you really liked it. If you liked it, please do press the like button. It takes a lot of effort and work to bring content, and that's a small token appreciation that I'll be very happy to receive from you. Thank you so much. I hope that the next video, which will be about recommendations and zero shot classification, will also be appreciated. Thank you so much.